14.7 talks about extreme values and saddle points. So saddle points are not a maximum nor a minimum. You don't need the graph to figure that out. We're going to figure that out algebraically. Extreme values mean maximums and minimums. So if we start with what a critical number is, just like C is a critical number if, what was it? F prime of C equals 0, or F prime of C does not exist. Do you remember that from algebra? In 3 dimensions, this is a bit different. A critical number of f of xy is the point AB in the domain of f such that f sub x equals 0 and f sub y equals 0. So if I take the partial with respect to x, set it equal to 0, and the partial with respect to y, set it equal to 0, this is a system of equations. Both of them have to be 0, provided the first derivative exists. Then that would be a critical number. And remember, a critical, not number, a critical point. A critical point could be a maximum, or could be a minimum, or it could be neither. You know, like you could find a critical number, y equal x cubed. You could say y prime equal 3x squared equals 0 and x equals 0. But we know from experience that that's not a maximum nor a minimum. So you could find critical numbers. You have to figure out whether they are maximums or they are minimums. And this table right here is provided for you on the test. You don't need to memorize that. What you do, you find this value d. What d is, evaluated at AB, it's the second derivative of f with respect to x evaluated at this point times the second derivative evaluated at AB minus the partial with respect to x then y, or y then x, because we figured from the last homework that f sub x y equal f sub y x, Claret's theorem. So the deal is, if d is positive, you're in luck. If d is positive, then you look at the second derivative of f with respect to x. If that's positive, the z value is a minimum. If that second derivative is negative, you have a local maximum for z. If d happen to be negative, if you do this combination and it turns out to be all negative, that tells you this is not a maximum nor a minimum. It's actually a saddle point. So direction is pretty much 2 sets of different problems. One with no limit, kind of like me saying, find the maximum or a minimum of y equal x squared. Well, without the graph, of course. You have to take the first derivative test and go from there. And that's kind of what we're doing here. This is, we know what that's the graph of. You don't have to know and what that's the graph of, but this is one of those. Of course, that's infinite. That doesn't stop there. That continues on, right? Well, we know this doesn't have a minimum, but it has a maximum. So let's see if that works. And it shows the first example to be straightforward to see this. So I take f sub x, which is negative 2x. And I take f sub y, which is negative 2y. Now, the deal is, I want this to equal 0 and this equals 0 at the same time. This equals 0 when x equals 0, and this equals 0 when y equals 0. So the point I got, the critical point, is actually 0, 0. That's the only point I got. Now out of those, I'll figure out what d is. To do that, I need f sub xx is negative 2. I need f sub yy negative 2. And I need f sub xy. Take a derivative of that with respect to y, that's a 0. So d is f sub xx times f sub yy minus f sub xy squared evaluated at this point AB. D would be at the point 0, 0, right? This is here. This is a negative 2, that's fixed. This is a negative 2, that's fixed. This is a 0 squared. I'm getting d to be 4, which means I'm in luck. It's either a maximum or a minimum. What's next? Take f sub xx, that's negative, which indicate f of 0, 0, which is, and you go back to the original like we did back in the days, that is 5, is a what? If it's negative, we agreed if it's a negative, it's is a local maximum. Now I know in this case it's the absolute, but to talk about absolute, which is the second half of this lesson, you really need to bound. Kind of like me saying y equal x squared has only one minimum. But if I say let's limit the domain and let x be between -1 and 2, now you're looking only at this portion of the graph. And now you take that local minimum, which you use calculus, you figure out f of -1 and f of 2. The highest of those will be an absolute maximum, and the lowest of those will be an absolute minimum. So here we're only finding local maximum, local minimum. Calculus allows you to do that. For the endpoints, you have to plug them in. And as you know, when we talk about a limitation, we're not talking about an interval anymore. We're talking about y being between certain values for 3D. So you're kind of looking at a portion of that graph. We'll talk about that when we get there. For now, let's get this out of the way. Here's another function. I don't need to graph. I could graph it. I could go to GeoGebra and sketch a graph of this. Or I could just say, well, let's do it first and then we'll look after. So I need the critical points. Let's take f sub x. F sub x is y minus 6x plus 2. Y minus 6x plus 2. The rest is 0. And f sub y is actually x minus 8y plus 2. This is a system of equations. I want this to equal 0 and I want this to equal 0. The reason I'm leaving some space, I still need to find f sub xx, which is a -6. And I need to find f sub yy, which is a -8. And I need to find f sub xy, which is a 0 in this case. So I need those values every time. Now what I need to know at which point am I going to have a local maximum or minimum. This is where I'm going to solve the equation y, well, let me put it in order. -6x plus y equal a -2, and x plus 8y minus 8y equal a -2. I could use substitution, of course, if I want, or I could simply say, let's multiply the top equation by 8. Wouldn't that become a -48x plus 8y equal -16? And if I add those, -47x equal -18. So x is 18 over 47, not a present number. And if I take any of those equations, let's say I take this equation, I'll get -6 times 18 over 47 plus y equal a -2. If I clear the fractions, I'll get, what is that? 48, 10, 108 negative plus 47y equal negative, what is that? 1494. So I'll get a bit more space. 47y equal, if I add 108 to this, I'll get a 14. Yeah, 14. And y would equal 14 over 47. So the points are a bit bizarre because I made these problems up. That's okay. So I have a critical point to be 18 over 47 and 14 over 47. If I made a mistake algebraically, You get the point. Now what? I need to figure out d. d is f sub xx, f sub yy minus f sub xy squared. d happens to be f sub xx is a negative 6. f sub yy is a negative 8. Minus 0 squared. d happens to be 48. So d is positive. I am in luck. And f sub xx is negative. Again, no need to memorize this. If f sub xx is negative, I'm getting a maximum again. I'm getting f sub 18 over 47, 14 over 47, and Aaron there figuring that out. That is 18 over 47 times 14 over 47 minus 3 times 18 over 47 squared minus 4 times 14 over 47 squared plus 2 times 18 over 47 plus 2 times 14 over 47 minus 2. This value would be a local max. And I got the graph to look like this. I sketched that in GeoGebra, and it's an upside down paraboloid somehow, and you do tell it has a maximum right there. You don't need to graph it. It's a good idea to look at it when you're done just to be sure that you see it. Here's another problem. I want to find the critical numbers. I would take f sub x, that is 2y. I will find f sub y, that is 2y plus 2x. I'll go ahead and find f sub x, that's 0, f sub x, y, that's a 2. I'll find f sub y, y, that is a 2. So these values I need for my d. Now, the system of equations. I want 2y to equal 0, and I want 2y plus 2x to equal 0. But here, if y equals 0, that's fixed. Put that there. I'll get x equals 0. The critical point is 0, 0. So I'm going to evaluate this if there's a need, add 0, 0, and up till now, that hasn't happened. d equal f sub xx minus times, let me put that down there because I'm going to sketch the graph and bring it to you, f sub xx times f sub yy minus f sub xy squared. d happens to be a 0 times 2 minus 2 squared. I'm getting that to be a negative 4. That means it's neither. Meaning no extrema. No local minimum or maximum. I'm going to graph that and bring it back in. And I graph that, and as you see, 0, 0. In one direction it is a minimum, and in this direction it's a maximum. It's a saddle point. Again, you don't need to graph those. It's a good idea to graph them to see it. Let's do one more before we move into the next idea. The same deal here. If I take f sub x, that is e to the y minus 3. If I take f sub y, that is x into e to the y minus 3. The whole thing, right? Let me think. This is actually x e to the y minus 3x. There. F sub x I got right. F sub y is x e to the y. My mistake. So let's go f sub xx, that's a 0. F sub xy, that is e to the y. F sub yy is x e to the y. That doesn't change. I need those values. Here, I need a value for x and y to evaluate those. Otherwise, that's going to be a problem. So the system of equations, again, a system of equations. E to the y minus 3 equals 0, and x e to the y equals 0. So keep in mind, if I take the top equation and say e to the y equal 3, that means y equal natural log of 3. I got a value. If I put e to the y equal 3 there, that will be x times 3 equals 0. That means x is 0. So my critical point is really 0 natural log of 3. Now, if I find d, which is f sub x, that's a 0. F sub y, that's e to the, times x e to the y, minus f sub xy, which is e to the y, but I need to evaluate that at the point 0 natural log of 3. This is being squared, of course. And this is 0 anyways, but this is going to be, if I put a natural log of 3 in there, I know e to the y is going to give me a 3 squared, which is negative 9 less than 0. So again, neither. It's a saddle. That's all you have to say. And I'm going to sketch a graph of that as well and show you that before I conclude this video and move to the next video. And as you see, this is also a saddle point. When I zoomed in the graph, the point was at x equals 0, but y was shifted to the left. I turned it around. Y was at natural log, and you could see in one direction it's opening up and in the other direction it's opening down. And that would be it for this video. I have one more to conclude this section.